Hi all, welcome to Engineers Think Box. This is Sharu. So in this video we'll discuss a problem on steady state output noise power, which is also called as input quantization error. So the question here is, an output of an analog to digital converter is passed through a first order low pass filter with the transfer function given by h of z is equal to 1 minus a into z divided by z minus a, where the a value lies between 0 and 1. Find the steady state output noise power due to the quantization at the output of the digital filter. So now this is the formula for the steady state output noise power. So sigma epsilon square is equal to sigma e square divided by 2 pi j closed contour integral of h of z multiplied by h of z inverse multiplied by z inverse into dz, where this value is there, right? Sigma e square, this value is equal to 2 power minus 2b divided by 12. That is, this will be equal to q by 12. This q value will be equal to 2 power minus 2b divided by 12. So now this is the formula here. In the place of h of z, we will be substituting this value as such, 1 minus a into z divided by z minus a. In the place of h of z inverse, in h of z, wherever z is there, I will be replacing it with z inverse. So it will be like 1 minus a z inverse divided by, here z is there again, so z inverse minus a. Then this z inverse will be placed here into dz. So now in the next step, what we will be doing is we will be calculating the poles. Poles are nothing but whenever a fraction is given, when we are going to equate this denominator part to 0, we will be calling it as poles. And if you are going to equate this numerator part, you will be calling it as zeros. So if we are going to calculate the poles here, so in order to calculate the poles, it will be like z. I will be equating this denominators, both the denominators to 0. So z minus a is equal to 0. So it will become z is equal to a. This is one pole. One more pole is z inverse minus a is equal to 0. So where you will be, this z minus a will be going this side, and it will be like z inverse equal to a. So z is equal to 1 by a. So here we have got two poles. For this equation, we have got two poles. That is, z is equal to a and 1 by a. So these are the poles. Now consider this unit circle. Unit circle is, we will be marking this unit circle on z plane, where it will be the values will be ranging from 0 to 1. So the thing here is, assume this a value, whatever it might be. So just assume it as a is equal to 0.5. In such case, so the z value will be 0.5. If I'm going to put it as 1 by 0.5 here, it will be z is equal to 2. So what I can conclude here is, a value, mod of a value will always be less than 1, and 1 by mod of a value will always be greater than 1. So when I'm going to place this and the unit circle, here I will be placing a and here I will be placing 1 by a. In most cases this will happen. And when one more thing which you should keep in mind is, the values which are inside the unit circle are considered to be as stable, and the values outside the unit circle are considered to be as unstable. So the thing is, the values inside the unit circle will contribute to the system, and the values outside the unit circle will not contribute anything to the system. So what the thing is, the values which are going to lie inside the unit circle, I am going to consider only that. So here the a value is lying between inside the unit circle, and 1 by a is outside the unit circle. One more hint which I can give you is, the real numbers, that is the integers will always lie inside the unit circle. If it is going to be a fraction, you can defaultly consider it as it will be lying outside the unit circle. This is just to identify in an easy way. Okay. So now what I'm going to do is, of these two poles, a and 1 by a, I'll be taking only a, I'll be considering only a, as it is inside the unit circle, and it is going to, it is stable, and it will be contributing to the system. So what I'm going to do is, I'll be calculating the residue for the system. So the thing is, this z minus z is equal to a I have calculated using this this thing, that is this this part of the equation. So what I'll do is, I'll be equating this, I'll be this multiplying this z minus a here like this, and I'll be solving it. That is nothing. In the residue part, 1 minus a z divided by z minus a into z minus a. Our ultimate aim is to cancel this z minus a, and we'll be dealing it with this thing. So what I'll be placing is, I'll be placing z minus a here. And here it is, here this will remain as such, 1 minus a z inverse divided by z inverse minus a, and this z inverse also will come here as such. This will happen when z is equal to a. Just in case, if you are going to consider by chance, if you are going to consider, you will not consider, but if in case if this is going to lie inside the unit circle, what you will do is, you will be removing this part, and what you will do is, you will be taking this thing, right? So you will be multiplying this thing, z inverse minus a, and you will be cancelling this both. Okay, I'm just giving it for for a better view. Okay, so in this case, you are going to consider z is equal to a only. So for z is equal to a, I will be cancelling this z minus a equation. So I will be multiplying it with z minus a. Here what will happen is, z minus a and z minus a will get cancelled, and inside this equation, wherever z is there, I will be substituting the value of z as a. So here it will, 1 minus a will come here as such, z value is a, 1 minus a will come here as such, z value is a inverse, again sorry, z value is a, so z inverse will be a inverse, z inverse will be a inverse, this z inverse will also be a inverse minus a. So now what will happen is, this 1 by a and this 1 by a, this 1 minus a and this 1 minus a will be clubbed as 1 minus a the whole square, and a and a inverse will get cancelled, and this a inverse will be retained as such. This a inverse can be written as 1 by a minus a. So now I am going to take LCM for this. The denominator will be a, and 1 minus a square will be the numerator. In the next step, what I am going to do, I will be taking this a to the numerator. This is just again a simple math. If it is going to be 1 by 1 minus, sorry, 1 divided by 1 by 5, you will be taking this 5 to the numerator, and you will be concluding it as 5, right? Same procedure here. So this a will be taken to the numerator, and if in that case, again this a and a inverse will get cancelled. Now this 1 minus a square can be expanded as 1 minus a into 1 minus a. This is in the form of a square minus b square. So the formula will be a plus b multiplied by a minus b. So 1 minus a, 1 plus b into 1 plus a into 1 minus a. So now if I am going to cancel this 1 minus a, this 1 minus a will get cancelled. So the remaining will be 1 minus a into 1 plus a. So now in this equation, this is the thing, that is, this is the equation which we are going to use for calculating steady state output noise power. Yes, so here what you have to notice here is, this thing is there, right, which I have marked. This is the formula for residue. These stuffs, if you can remember it, you will be dealing it with first year engineering mathematics. So the formula is 1 by 2 pi j into contour integral of h of z inverse into dz. So for all this thing, I have solved it, and I have got the answer as 1 minus a divided by 1 plus a. That is the residue answer. Okay, now the remaining thing is this thing, sigma e square. We know that sigma e square formula is 2 power minus 2b by 12. Actually, the original formula is sigma e square is equal to q by 12. This q value is where this q value will be 2 power minus 2b. So this is 2 power minus 2b divided by 12 into 1 by, say, 1 divided by 1 plus a. So this is the final answer for the steady state output noise power. In the next video, we will be discussing product quantization error and coefficient quantization error. Stay tuned. Thank you.